bridge unmuted, right? So I think we can go ahead and continue with the presentation. But of course, we'll give you more opportunity toward the end of the session to ask questions using the audio bridge. But of course, you also have this questions box, so feel free to submit your question. Okay. Oh, okay. Yeah, for those guys still wondering, yes, the plan is still to complete our session material before 5. Okay, 5 o'clock Eastern time. Oh no, not Central time. Central time. Yeah, you have to wrap up in 10 minutes. Okay. So let's see transmitter. So now we'll see how the OFDM transmitter and receiver work. Okay. So we have some user data. Again, this is simplified version. Okay. So we have some user data. We do the data protection. Basically, add some redundancy, such as through turbo coding. Do the modulation. In this case, we are doing 64 pumps. So one modulation symbol represents 4 bits. The modulation symbols are then given to the channel mapping. So one modulation symbol goes over one subcarrier, another modulation symbol goes over another subcarrier. And then we give those modulation symbols on orthogonal subcarriers to IFFT. And this is the inverse fast Fourier transform. And this IFFT will combine all the orthogonal subcarriers carrying modulation symbols into this strange looking signal. But inside the strange looking signal, we have orthogonal subcarriers, each subcarrier carrying one modulation symbol during that OFDM symbol period, which is in LT about 66 microns. Okay, so effectively that goes over there. We are not showing the other parts such as filtering. Actually, you add cyclic prefix, then filtering and frequency up conversion, but they will be there. We are just trying to highlight the baseband portion of the major processing. So at the transmitter, the main processing block is this IFFT. And this IFFT will combine the subcarrier into this one OFDM symbol. And as I mentioned earlier, over the air, OFDM symbols are being transmitted. At the receiver, we do the opposite process. But if you are interested in the IFFT, then here is the formula. IFFT basically is a fast way of implementing inverse discrete Fourier transform, and here is the formula for the inverse discrete Fourier transform. We have the modulation symbol, and that symbol is basically intended for this subcarrier K. And we are basically going from the frequency domain, because we are going from subcarriers to the time sample. So basically we have modulation symbols here going over various subcarriers, and inverse discrete Fourier combining them using the formula, and now we get the time sample. So this kind of time sample, this would be time sample 0, time sample 1, the last value, let's say somewhere here. That's what we do. Okay, so this is giving us the structure of the signal that will be transmitted over the air. At the receiver, we do the opposite processing, as I mentioned. So at the transmitter, we do IFFT. Okay, So at the receiver, we do the opposite of that. So it is fast Fourier transform. The IFFT took the modulation symbol, right, and it gave us the strange looking signal. Here, it's the opposite way. Strange looking signal will go in, and you will get back your modulation symbol. Then we do the demodulation. So you recover those modulation symbols over orthogonal subcarriers. Then you opposite of channel coding is decoding, and now you will get back your user data. So in summary, IFFT at the transmitter and fast Fourier transform at the receiver. These are the key building blocks for OFDM system. Okay, that's the important piece of it. Again, if you are interested in the detailed structure of FFT, FFT is nothing but fast way of implementing discrete Fourier transform. So in the discrete Fourier transform, you have the time samples going in, and you will get back your modulation symbol. So this kind of signal is received, and you are taking all the samples, right? Those samples are here, and when you combine the samples, you will recover your modulation symbol. That is the basic idea. Okay, this should be simple enough, should not take us long. So can you please submit response to this question? Let's aim for maybe 2 minutes, 1 to 2 minutes for this. So inside that strange looking signal that IFFT gives you, inside that, do we have orthogonal subcarriers that have modulation symbols? So yes or no, true or false? So think about the strange looking signal. Inside that, do we have orthogonal subcarriers that have modulation symbols? What is OFDM symbol, right? Inside that, what do you have? What will you find? And now the electronics is ready, capable of doing those IFFT, FFT type functions very, very quickly. We can do channel estimation and so on. So even for mobile environment, we can meet the performance requirements. So that's why now it is good time to exploit this kind of technologies such as WebKit. A few years ago, we did not have capability to do this quickly, but now the technology is available to do this kind of processing. Okay. The correct answer is true. So we have IFFT signal. Let me just go back to the transmit. Okay. So this is the transmit, IFFT. It gives you this kind of strange looking signal. But inside that, we have these orthogonal subcarriers. One subcarrier carrying one modulation symbol. So hopefully now you are okay with that. Okay. Now I will give you an example of how we could potentially design a generic OFDM system. Now this specific example is based on wireless LAN 802.11. Okay. For LTE, I will discuss design parameters in the next session, session number 3. Okay, so the requirement is to support 20 megabits per second data. The delay spread is 200 nanoseconds. So basically 0.2 microseconds. available bandwidth 15 megahertz, and there is a dozen subcarriers basically that cannot be used for data. So this is what we are given, and we need to meet the requirements of this kind of data. Okay, so let's look at the example. Now we talked about the cyclic prefix, right? We just need to make sure that it is greater than the delay spread. In wireless LAN systems, we have a little bit larger factor. So we say in this example as a rule of thumb that 4 times the delay spread. But we do not do that in cellular, okay, not in cellular. This is fixed wireless environment, so we are doing that. Okay, this is an example for that. Okay. So for this example only, we said, okay, let's have enough cyclic prefix guard time. So 4 times the delay spread. So 4 times 200 nanoseconds, this is given to us. 800 nanoseconds, 0.8 microsecond, that is your guard time, inside which you will see cyclic prefix, cyclic extension. We want to make sure that we do not have too much overhead. We should have enough time to send our useful symbol, our modulation symbol. So here again we have some sort of rule of thumb that says maybe 6 times the guard time. That is pretty good time for the actual information. So okay, 6 times the guard time, that gives us 4.8 microseconds. So we have total symbol time 4.8. That is the total symbol time. And out of that, 0.8 is for the guard. So the remaining time period is your useful symbol time or your modulation symbol period. So that would be your 4 microsecond value. Okay. Now we know the relationship between subcarrier spacing and the symbol time. Remember we had that poll question. Okay. So subcarrier spacing 1 divided by the time period. 1 divided by useful symbol time, which is the modulation symbol period. 1 divided by 4, that will give you 250 kilohertz. So that would be your subcarrier spacing. Since we are given 15 megahertz, we will be able to squeeze in these many subcarriers, 15 megahertz spectrum divided by the spacing, 60 subcarriers. But not all of them are available for data. We mentioned that a dozen subcarriers are your overhead kind of subcarriers. So the usable subcarriers, 48. Okay. Now you want to do high order modulation because we want to get pretty good data rate, 20 megabits per second. So let's say we use 16 QAM. And of course, 116 QAM modulation symbol represents 4 bits. So now we have 48 subcarriers, meaning 48 modulation symbols. Each modulation symbol 4 bits. We have 192 bits we can send. How much time do we take? Total time. So 192 bits. And the total time, including your guard time or cyclic prefix, the total time is 4.8. So we will get 40 megabits per second. We just need 20. No need for 40. It means we can add some redundancy. So we can do half rate channel coding. So 20 megabits per second. So basically we have 20 megabits per second data rate going into the coding block, half rate coding. That will give us 40 megabits per second. Okay. And we will have then modulation, right? 16 comma modulation symbol, and you will get 48 modulation symbols during the time period of 4.8 microseconds. So one modulation symbol will go one subcarrier, another modulation symbol another subcarrier. A total of 48 subcarriers will be used to send the 48 modulation symbol. That is the basic idea. This is a generic example, so that's why we just use 16 comms. Okay. However, the LT itself supports 64 com. That is correct. Okay. LT supports 64 com. For this example, 16 com is good enough because it's a generic OFDM system. Okay, we have one question. 300 megabits doesn't include redundancy. So if you recall, let's go back quickly. So that 300 megabits per second indeed had some redundancy. So if you look at this picture again, you will see that we have here. Okay. Looks like okay. It's a little bit slow, but now you should. Okay. So yeah, 400 megabits per second. Right? It was 100 multiplied 4, so we do have redundancy. Okay. Very good. Just type in your question, okay? Anytime you have a question, just send it my way. Okay, so this is how we can get 20 megabits per second. And again, it was for wireless LAN type system. LT we will discuss in the next session. The parameters that are specific to the LT. Okay, so we have talked about orthogonal frequency division multiplexing, so for OFDM. Then what is this OFDMA? Right. So we have multiple access, orthogonal frequency division, multiple access. Okay, now very simple idea. At a given time instant, let's pick this time instant, we are able to use the system such that we can support not just one user but many users. So in this case, at this time instant, we are supporting 3 users, 1, 2, and 3. Okay. So one user we have given, let's say, 900 subcarriers, so very high data rate. Another user, let's say, 99 subcarriers, so this guy gets about 1 megabit per second, and some voice or IP type users, maybe 10 kilobits per second, good enough. So at a given time instant, we are supporting multiple users. And whenever you support multiple users, it's called multiple access. If you focus on, let's say, mobile station 3, then we are sending the data to the user using many subcarriers. In this case, 900 subcarriers. Since we are using multiple subcarriers between the base station and the user, we are using OFDM. So we have OFDM between the base station and the user, OFDM between another user and the base station. But from the overall system's perspective, since multiple users are able to access the system at the same time, then we say that it is OFDMA. If you have parallel transmission on multiple subcarriers, you are using OFDM. And when you have OFDM for multiple users, it becomes OFDMA. So that's the minor distinction between OFDM and OFDMA. In general, we have this opportunity of doing an exercise to calculate the data rate. But today we had a lot of questions. Okay, so let's see how we do in terms of the time. So once we are done with all the material, if we still have some time left, then we will do the exercise. Okay, so for now, we will skip that, but we may come back later. Okay, depending on how well we do. Okay, the remaining slides, because we want to make sure that we cover all the basic material. And for the data exercise, at least you have some idea, okay, of the calculation. We already did one example. So for now, let's skip, but we may come back. Okay. Okay. From the LTE's perspective, we support frequency duration duplexing. So let's say 10 megahertz uplink, 10 megahertz downlink, like together 20 megahertz. So that's one way to operate an LTE system. Another way is use time division duplexing. So you have the same 10 megahertz bandwidth. Sometimes we use the bandwidth for downlink, sometimes the same bandwidth for uplink, and so on. So at any given time, we are using the bandwidth either for uplink or for downlink, not two at the same time. In FTD, we can do up and down at the same time. There is a special case of FTD, so-called half FTD. Half. So basically, here we have some possibility of supporting some low-cost device. So these devices, they can support two spectrum, two carriers, uplink and downlink. So they can tune to two RF carriers. So that is not a problem. But they can do only transmit or receive at any given time, not both at the same time. So for example, if you pick this time instance, this user is getting data in the downlink. It is not transmitting. And in the next time instance, this user is using the subcarrier here, let's say FX and FY. It will use carrier frequency FX for uplink transmission. It used another carrier frequency FY for the downlink reception. So as you can see, it is not doing both transmission and reception at the same time. It can do only one of the two at a given time instance. And the reason is that these are low-cost devices, okay, and that's why they do only one kind of processing. I'm not aware of any LT devices yet that do this kind of stuff. In my opinion, we will see the traditional FTD kind of device in the initial deployment. But maybe in future there may be these kind of devices, low-cost devices. We have the difference between half FTD and TDD. What is the difference between the two? Okay, the difference is here you have only one carrier frequency FX. Right? You are not tuning to different carrier frequencies. Same carrier frequency FX. Here you have one part of the spectrum for uplink, another part of the spectrum for downlink. So uplink is FX and downlink is FY. You have two different frequency spectrum. So from the base station perspective, it is doing transmission reception at the same time. For a given UE, we are doing transmission or reception, only one of the two. So hopefully the difference is clear. Here we have single carrier frequency in TDD, but here the UE indeed supports two different carrier frequencies. But it will be on one carrier frequency at a given time. Oh, look, couple of other questions. Any latency difference between FD and TDD? Yes, of course, since we have to sort of wait for our turn, throughput and latency will be slightly degraded in terms of user perceived experience. It may or may not matter much. Depends on the services. So if you have reasonably good pipe and we can ship out data to the user quickly, then it may not matter a whole lot. But when you have lots and lots of users, right, then we may start seeing some impact. But in general, FTD, the benefit of FTD is better throughput, lower latency, better throughput, reduced latency on average, and the drawback is, of course, we need more spectrum. TDD, yeah, so change this plus to minus, right, and this minus to plus. We need less spectrum, right? 10 megahertz. Just a single chunk is good enough. Someone has this comment that, oh, FTD is a must because we need full duplex to support voice or IP calls. Well, you can do voice or IP even here. Okay, because this time period here is not a whole lot. So we are talking about microseconds here, not milliseconds. So you can you can send a voice frame, you can receive voice frame very, very quickly. So it is okay. Even TTD you can do voice or IP call. As long as you transmit and you can receive, maybe not exactly the same time, slightly off by some microseconds. We are okay. But if you have any follow-up question, just let me know. But from VoIP perspective, it's okay. We can do either because this is not some long time. It is very, very fast switching between uplink and downlink. Okay, the question is what to use. Then now, normally what happens, essentially is a matter of operator preference and how much bandwidth the operator has. Traditionally, close to 100% of cellular networks are FTD based. Okay? That's what 1X, 1X video, UMTS, GSM, etc. have been. And same thing will happen. The initial deployments of LT in the US, they will all be FTD. I have heard that in China they are focusing more on TDD, but at least in my opinion, FTD will be more prevalent. Okay, easier to make FTD work. If you are doing TDD, then you have to worry a lot about interference because one base station's downlink may become another base station's uplink and so on. So there is a significant possibility of having very, very high interference. Okay. So your signal will be buried inside the interference. If you do not plan properly. So that's why TDD is more complex. FTD, we have separation of downlink and uplink, easy to manage. We have experience with that, so that's why FTD will be more prevalent in my opinion. Any other questions, just send me email. Spectral efficiency, same for FTD till bits per second. Spectral efficiency. Okay, I'm trying to calculate the time. Okay, we have the time aspect. Okay, now it depends how you want to sort of handle. If you have, let's say, 10 megahertz downlink and 10 megahertz uplink, so you are using total of 20 megahertz spectrum, FTD, right? So if you want to get similar spectral efficiency, you could say that, okay, you will have 20 megahertz TDD, and maybe you will allocate 50% time to the downlink, 50% time to the uplink. Yeah, so then you can get the same spectral efficiency. But it depends on your assumptions. So hopefully this information will help you. Okay. Okay, if the answers are inadequate, you need more, send a follow-up question. Okay. And again, thank you for the question. Okay. Oh, and we already mentioned that in the downlink we have traditional OFDMA, in the uplink we have a variation of that called SC-FDMA. Okay, so LT specific parameters, we are already familiar with many of those. Cyclic prefix, we already know that, right? Two values, a short one and the long one. So depending on the delay spread, we will choose that. Then two frame structures, FTD, one is for FTD type, another for TDD. Advanced and non-techniques are supported, we know that. Spacing, we already know, 15 kilohertz, right? The bandwidth, we said that is scalable, as little as 1.4, as wide as 20 megahertz. Some other values in between also supported. We have a question. Oh, someone has this question. If we sync, oh yeah, and of course the E node B's need to be synchronized in TDD. Now, if we have a uniform way of implementing the scheduling algorithm, meaning that once, okay, first of all, in general, one scheduler in one base station is independent from another scheduler in another base station. So if you let those independent schedulers choose the uplink and downlink slots, then you are inviting troubles, because one base station's uplink may become another base station's downlink. Now, one student has a comment that, oh, if we synchronize, then will that solve? So, as long as you have configured those schedulers that, oh, they will never allocate slots differently, so then basically you have to predefine that these time slots for uplink, these time slots for downlink, and so on. So then you will be okay. Then you can solve that problem. However, see, if you do that, that will defeat one of the main motivations behind TDD, and that is that, oh, we can have asymmetric link. We can have, based on the traffic, maybe we can give more slots to downlink, fewer slots to uplink, and so on. So, of course, to solve the interference problem, you have to configure the scheduler. Then you are not fully utilizing the TDD potential. But of course, if you try to fully utilize TDD potential, then we run into interference problem. So basically, as a vendor and as an operator, you have to basically choose, right, how you want to operate. But yeah, it's possible through configuration to force certain slots to be uplink and downlink, and then you are okay in terms of interference. Okay, thanks for your question. Let's move forward. Okay. Type 1 frame structure and best focus in the Bootcamp series STD. So we have a 10 millisecond frame. Inside the 10 millisecond frame, we have 10 subframes, 0 through 9. Of course, every subframe is 1 millisecond long. We already know by now, based on our questions and answers, that inside a subframe we have 2 slots. Each slot is half millisecond long. Now you may be wondering why we have all kinds of timing structures, why frame, why subframe, and why this kind of slot. Subframe. That is for resource allocation. So every subframe, early part of the subframe here, we will have some sort of control channel. Okay, we also mentioned that as part of the answer to one of the questions, that this control channel will provide the resource allocation. And that is the reason that we can change things around every millisecond. So during this millisecond, I can tell you that I will give you 100 megabits per second. The next time, oh, I will give you 1 megabits per second. Next time, I will give you 3 megabits per second, and so on. So we can change things, change the data rate every millisecond in LTE. If you want to do that in WiMAX, you can do that every 5 milliseconds. But LTE helps you react faster, and you can do that quickly every millisecond. So we know why we have subframe. Why do we have slots? One of the main functions of the slot is after power on, our UE is trying to synchronize with the network. So the slots will help us with the synchronization after UE is powered on. No need to worry about the details. We will cover that in one of the future sessions. But for now, it would be good enough to know that, okay, slots are useful for synchronization. So we know why we have slots, why we have subframes. Why do we have these so-called frames, 10 millisecond long frames? The information about the system is sent in the units of frames. So let's say you want to convey to the user that the system bandwidth that we are using in the cell is 10 megahertz. So that kind of information is sent in so-called master information block, and that will be using the unit of frames. So that's just one example. But basically, information related to the system is sent in the units of frames. In summary, slot for synchronization, frame for system information, subframe, resource allocation. Those are some of the main functions of those timing units. Okay, now let's look at the transmitter that is defined for LTE. In LTE, we have this user data information bit, and we do the coding. And then we do the interleaving. Okay, so now we have here code symbols that have been interleaved. So whatever comes out of the coding and we have processed through interleaving, that is your code word. So this is your code word. In LTE, we have up to 2 code words. So you can have 2 parallel turbo coding blocks. So you can have the same thing here, information and turbo coding or whatever, right? Whatever rate, etc. So that will give you code word number 2, another code. So we have 2 code words now. You can do scrambling. So for example, you can scramble the information using a lot of parameters. So one would be the identity of the cell. That will be one of the inputs, just one of the inputs. There are many inputs. So we scramble the bits, do the modulation. What is the highest order modulation for LTE? Highest order. Just making sure that you are awake. 64 count. Very good. Thanks for your answer. Someone is very fast in typing. Answer received very quickly. 64 count. Then we have something called layer mapping and pre-coding. Do not worry about this too much, but I will give you the basic idea. This is basically to support advanced antenna techniques. we have one whole session dedicated to advanced antenna techniques. So we'll revisit this at this time, but basically, we have advanced antenna techniques. To support those, we will have this kind of processing blocks. Okay, so here we have some sort of code symbol, some sort of modulation symbol. Because we did the modulation here, so we have some sort of way of modifying modulation symbols, perhaps, and then we will have those modulation symbols going into so-called resource element mapping. Now, what is this resource element mapping? One resource element basically has one subcarrier and one modulation symbol. Okay. So if I have, let's say, symbol 1, maybe I will put that on subcarrier 1, symbol 2, I'll put that on another resource element, another subcarrier, and so on. So that's what we are doing here. Then OFDMA symbol generation, this is your IFFT. So you are combining all the modulation symbols on all subcarriers, and then this kind of strange looking signal will be going out. Similarly, you can do IFFT for another branch that you have for second code word. Then maybe also like that. You could have up to 4 antenna transmission. Here we are just showing you 2, right? But there could be up to 4 IFFT blocks sending out the signals from the antenna. At the receiver, we will do the opposite process. Let's look at the uplink. Uplink, we have variation of OFDMA, so-called SC-FDMA. Okay. So what do we do in SC-FDMA? We have some modulation symbols. Rather than giving those modulation symbols to the IFFT, we do extra process. So basically now we are doing so-called DFT. So DFT, IFFT, right, are mathematically the same. So you are basically giving the modulation symbols to this DFT block, and you get some sort of complex numbers here coming out. So your modulation symbols are now transformed into some sort of complex numbers based on the DFT formula, and you already know the formula. It is in the PDF file that you have. But we have some sort of transformation of modulation symbols. Then let's say we call complex number 1, C1, C2, etc. We have some complex numbers. We give one complex number to one subcarrier, another complex number to another subcarrier, and these are all orthogonal subcarriers. Then we do the IFFT. This is your regular IFFT. Now see what is happening. You are following this DFT by IFFT. DFT followed by IFFT. And they are opposite processing. Right? One is the inverse of the other operation. So essentially, what comes out is something like your original modulation symbol. So something like that, some transmitted signal comes out, and this is basically some sort of modulation symbol. Okay. Now let me draw a picture to illustrate why we are doing that. What is the basic idea behind that? Okay, so to provide us motivation for SC-FDMA, let's see what this regular OFDMA IFFT doing. IFFT. Okay. You have F1 sending out one modulation symbol, then F2 sending another modulation symbol, and so on. These are all orthogonal subcarriers carrying your modulation symbol. Okay. Now let's observe the signal that is coming out of this IFFT. Okay. So this is 406 something like that. Okay. Okay. So let's observe the amplitude of the signal at this time instant. The amplitude of the transmitted signal at a given time instant is a function of all modulation symbols. So for example, here it will be alpha times modulation symbol 1 plus beta times modulation symbol 2 plus gamma times modulation symbol 3 and so on. Okay. So, and these alpha and beta and gamma, basically these are your IFFT coefficients based on the formula that I had shown you earlier. You can map that to some coefficients. So at any time instant, the amplitude is a function of all modulation symbols. So you are adding up with some sort of weights. And since all these numbers, let's pick either this or this, right? Essentially these are random numbers. You never know about the bit pattern. So for all practical purposes, it's a random number. So here you are adding up those random numbers, and that's why you see high peak to average power ratio, because you are adding up those random numbers. Now let's talk about this SC-FDMA based on the diagram that we just saw. So we did DFT and we followed that by IFT. So since these are inverse operations, essentially whatever you send to the DFT, that is effectively coming out here. So if I observe the signal that is being sent out by the IFFT, okay, so here is my signal coming out, and now I will observe the amplitude at this time. So amplitude of the signal at this time is a function of one modulation symbol rather than function of all modulation symbols, because these operations are effectively inverse of each other, right? So if you have some number 10, if you multiply by 2, right, then you divide by 2, right? You are doing the opposite process, inverse process. Then you will get your original number back. Same idea, you have DFT, IFFT, inverse operation. So you will retrieve your original modulation symbol. So because of that, the amplitude is no longer a function of all modulation symbols. It's a function of one modulation symbol. And now you are no longer adding those random numbers, right? In the IFFT, we were adding up those random numbers, right? Modulation symbols. But now you are no longer doing that, because these are effectively cancelling out. So because of that, we have reduced peak to average ratio. We are no longer adding up those random modulation symbols. That's the beauty of SC-FDMA. In summary, in SC-FDMA, the advantage is lower peak to average ratio. The disadvantage is more complex, because we have this extra processing of DFT. We have extra processing both at the transmitter and the receiver. So at the transmitter, we are doing DFT. There's the new stuff we need to do. And at the receiver, we need to do opposite processing. Okay, so it will make the system more complex. That is the main advantage and disadvantage of SC-FDMA. But the advantage is, of course, reduced peak to average power ratio. That's why we have chosen to use that for our uplink LTE. Okay, let's go one step further. Transmitter, so basically just like before, we have information bits, do the coding, do the interleaving, right? And now you have code symbols coming out that have been interlinked. Give that to the scrambling block, the modulation. Again, uplink also has highest order 64 com. So both uplink and downlink can support 64 com. Transfer precoding, this is your DFT. Here the complex numbers coming out, they are sent on specific subcarrier F1, F2, etc. Here we do the IFFT, right? And the combination of DFT and IFFT will give you transmitted signal that has lower peak to average power ratio. That is the overall change in terms of the transmitter. How do we support multiple users? One set of users here, we are given one block, so a dozen subcarriers, let's say 12 subcarriers. Then we have another user, we give another set of subcarriers. So different users can be allocated different sets of subcarriers in the uplinks, and that's how we will be able to separate them. So just like the downlink, we have different subcarriers for different users. Same way in the uplink, we allocate different subcarriers to different users. We already know why SC-FDMA. Basic idea is it will reduce peak to average power ratio. If you are able to reduce peak to average power ratio, you can exploit that in a couple of ways. For example, you can say that I would keep my maximum power same, so I will not touch the maximum UE power. So if you keep the same maximum power, then you will have better link budget, and then you can support larger cells. If you have fixed cell size, maybe you are reusing your 1xc video cells or UMTS cells, so you are not changing the cell site location, then it means because we have better technique in the uplink, compared to OFDMA, we'll get better performance at the cell edge. Okay. So this is if you keep the maximum power the same. However, you can say, oh, I want to reduce the cost of the device, so I will buy lower rating of power amplifier. If you buy lower rating power amplifier, then you will reduce the cost of the UE. So these are two basic ways in which you can exploit API reduction. Either you can keep the power same, cost the same cost, and that will basically give you better performance. Or you can say that, okay, I want to save money, okay, compared to performance, then we can always buy lower rating power. But that's the main idea. SC-FDMA will reduce peak to average power ratio. Let's see what time for. Okay, we should be able to do this. Okay, what is false here? And in the meantime, we have some questions. So once you are done with this poll, we will then take care of the question. So there is one person, input is multi, then what? Oh, okay. Yeah, so, okay, good question. Yeah, we have two good questions. We'll answer those once we are done with the poll. Please participate in the poll. Some of you are on a break, looks like, or some meetings. Only 12 so far. Maybe you are thinking. Please participate. So far we are on target, okay, to complete the session in time. So don't worry about that. Okay, I will give you a couple of more minutes. Looks like some of you are working on it. Very good. Okay, maybe I should give the answer in the meantime. You are providing this answer. Okay, okay, remember, this SC-FDMA is for the uplink. Okay, for the uplink. And the user has some modulation symbols to send. So, whatever subcarrier base station has allocated to that user, the user will use only those subcarriers. So one set of subcarriers for one user, another set of subcarriers for another user. So this IFFT in the uplink is done independently by different mobile stations. Okay. So one user equipment does its IFFT, another user equipment will do its own IFFT, but the subcarriers that they will use will be different based on the allocation. So hopefully that will answer your question. Another very good question, does the user get some subcarriers that are contiguous? So the answer is yes. For the uplink, we have contiguous subcarriers allocated to the user. You can do frequency hopping in the uplink, okay, but you do have contiguous subcarriers in the uplink. In the downlink, you could have allocated, let's say, different parts of the spectrum to the user. So you can give left part of the spectrum, middle part of the spectrum, then right part of the spectrum to the same user. So in the downlink, that is possible. In the uplink, we stay with consecutive subcarriers. And remember, here we are looking for incorrect answer. Okay, incorrect, not the correct. False. We are looking for a false statement. So most of the statements, actually all statements except one, are correct. So false. We are looking for a false statement, not the correct statement. So maybe some of you are reading this incorrectly. Okay, let me share with you the results. Okay, so looks like we are reaching our saturation threshold. 66% gave the correct answer. Maybe you misinterpreted the question. See, we are looking for a statement that is not correct, that is false. So the first statement is of course right. We are using OFDMA in the downlink, so that's good. SC-FDMA in the uplink, good. The main reason that why we are using SC-FDMA is to reduce peak to average power ratio. So that is also correct statement. OFDMA reduces peak to average power ratio. That's exactly the opposite of what we know. Actually, SC-FDMA is better than OFDMA for peak to average power ratio reduction. Okay? So that is incorrect statement. Okay, OFDMA does not give you lower PAPR. SC-FDMA gives you lower. And the last statement is correct. You do have more processing blocks. Remember, we have DFT, that is the extra processing block. So I mentioned that the drawback of SC-FDMA is that we are doing this extra processing at the transmitter and at the receive. That is the main drawback of SC-FDMA. The advantage, of course, is that it reduces peak to average power ratio. So hopefully now things are very clear. Okay. Okay. So let's unmute the bridge at this time and see if there are any questions. There is one very good question remaining, which
The
is
conference has been unmuted.
why 66 microseconds. Okay, so basically that gives us 15 kilo spacing, subcarrier spacing. And I will give you the two competing goals that we have. Okay, if you have wider spacing, then it's better for high-speed users, better for fast-moving vehicles. So from that perspective, we like that. However, if you have narrower spacing, then we have a simpler receiver design, because the subcarrier will experience flat fading. So it's easy to do channel estimation and recover the information. So easier channel estimation. Okay. If you have a wider subcarrier spacing, then you are more likely to experience frequency selective fading, and that will make your receiver design more complex. So that's the trade-off that we are trying to get. Right? If you have very wide, your intercarrier interference resistance is pretty good, right? However, if you're narrow spacing, then it's giving you simpler receiver design. So the trade-off between the two is, for LT, they have chosen 50 kilos. Okay? But that was a very good question. Okay, any other questions? Any question at all? But of course, thank you very much. You asked many questions. Good questions. So thank you for that. Hopefully you learned quite a bit today. At this time, we would request to send evaluation form your way.